Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants, and today we are talking about naming compounds. So let's begin. We're given the instruction to name the following compounds. Well, this compound in particular is an ionic compound. The main thing to remember whenever dealing with most compounds that don't involve complex ions is to add an IDE at the end. Now, you can readily see that this isn't going to be an easy compound to name. We have Mg, which is magnesium, and we have oxygen. So, adding an "ide" at the end, we come up with oxide. And that's the name for this first compound. Recall that every time you name a compound, every time you write the formula for a compound, it always goes cation to anion. Anion always follows the cation. And in order for any compound to exist without a charge, its charge must effectively be 0. So let's look at the next one. The next one is a little complicated, or a little more complicated. Whenever you look at these particular compounds and you see more than 2 species of element, automatically assume that you're probably dealing with a complex ion. When you look at your table of complex ions, you'll find that ClO3 is actually named chlorate. So that's half the battle right there, knowing that ClO3 is chlorate, and recalling that with complex ions, you do not add the IDE at the end of the anion. Otherwise, it would be chloride, and that would denote just the chlorine and not the 3 oxygens. That's why you have to call it chlorate. The next thing to look at is our cation. The cation is copper. So we know that this is going to be named copper something chlorate because this is an ionic compound. It has an anion and it has a metal. It's a non-metal plus a metal makes it ionic. So it's going to be copper something chlorate. Now, to determine what that something is, you have to recognize that the charge on this whole molecule has to be 0. And in order to determine that, you have to put the charges on the different species. Now, copper sits in the transition metals, which means it can carry a couple of different charges. And we don't know what the charge is going to be. So, if you put this off to the side, we know that Cu is going to have some positive charge. And we know that ClO3 has a given negative charge. If you look it up in your book, you'll find that chlorate has a -1 charge. But the story's not over yet. Note over here that we have a 2 at the end of the chlorate. That little subscript of 2 following the parentheses indicates that there are 2 of the complex ions that are enclosed within the parentheses. So that's like saying there are 2 chlorates. But we don't call it dichlorate or anything like that because it's an ion. It's an ionic compound. We're not worried about using the prefixes that you would if it was a molecular compound. molecule. So, in order to make this 0, we just have to do some very basic algebra. We're going to call the charge on copper X. And then we want to add to X whatever the charge is on chlorate, and whatever the ultimate charge should equal, it's going to equal 0. So we know that chlorate is a -1, but we also know that there are 2 of them. So that's like saying X minus 2 is equal to 0. Well, if you just add 2 to both sides, you find that X, which is our charge on copper, is 2. And it's positive, which fits the goal of copper being a transition metal. It should always have a positive charge. So, when dealing with ionic compounds that involve transition metals, we have to include the charge on the transition metal in Roman numerals within parentheses following the transition metal. It seems like a lot to say in a very short period of time, but all that means is that it becomes copper, parentheses, the Roman numeral 2, chlorate. That's all it means. And that's the correct name for this compound. Our next one, again, involves several species. And because there are more than 2 species involved, we're going to go back to our original assumption that there's probably a complex ion involved. And in fact, in this case, there are 2 complex ions involved. There's NH4 and NO3. If you look in your book, NH4 has a +1 charge and is called ammonium. And NO3 has a -1 charge. It's called nitrate. So, our compound is just ammonium plus nitrate. So, it's just ammonium nitrate. Simple as that. Not too bad at all. And note that the positive charge on ammonium cancels with the negative charge on nitrate to give it a 0 charge, which is exactly what we wanted. Next one that we have is K2Cr2O7. Wow, that's quite a big molecule, but not the biggest I've ever seen. And furthermore, it involves more than 2 species of atoms. So, if you look in your table of complex ions, you'll note that Cr2O7 has a name, and it's called dichromate. Cr2O7. Dichromate. And it has a -2 charge, which makes sense because there are 2 potassiums, which is this K up front. And because there's 2 of them, and we know that potassium has a +1 charge because it's in the group 1, we also know that potassium is going to have an ultimate charge of +2, which cancels out with the dichromate, giving us a net charge of 0. So the final name for this molecule is going to be potassium dichromate. And again, it's ionic, so you do not put the prefix on potassium. Okay. Let's look at some other types of problems you might encounter. Write the chemical formulas for the following compounds. The first one that we're given is potassium dihydrogen phosphate. That seems like a lot, but let's take a look at it. It should be kind of easy. So you'll note that phosphate is a complex ion, and it's denoted as PO4 with a -3 charge. We know that potassium is a K with a +1. So now we're looking at dihydrogen. All that means is that there are 2 hydrogens. So there's 2 hydrogens. Well, we don't like this coefficient out front, so we're going to drop it down into a subscript, making our final equation, final formula as KH2PO4. The +1 and the +2 from the 2 hydrogens cancels out with the -3 from the phosphate. So we're left with KH2PO4. Let's look at another one. Mercury 2 cyanide. Again, this is an ionic compound. Cyanide is a complex ion denoted as Cn with a -1. Mercury is a transition metal, so it can carry different charges depending on the situation. And in this case, we're going to determine that it's a 2 charge on the mercury. So mercury is denoted as Hg with a 2+. Well, these have to fit together and create a 0 charged compound. So in this case, mercury 2 cyanide would have to have a corresponding negative charge to counteract the positive charge. So we're going to write it Hg for mercury, and then we're going to put parentheses Cn, and then in order to make the Cn cancel out the Hg, we have to have Cn at a -2. Well, right now it's at a -1. So if we had 2 cyanides attached to the mercury, then it would cancel out the charge on the mercury. So we just put a little subscript of 2. And that's mercury 2 cyanide. Not complicated. The next one is calcium nitride. Not too complicated. The only thing to look at when you're doing this one is at what is the lowest values that these 2 charges on these separate species cancel each other out. So calcium has a +2 charge, and nitrogen, which is nitride and is actually just nitrogen, has a -3 charge. And sometimes you have to play around with these a little bit to find the least amount that you can fit it into, especially if you have more than 2 species. But in this case, it's pretty obvious. In order to get this to equal 0, you have to have 2 times some number minus 3 times some number equaling 0. Well, the only way that's going to happen is if there are 3 calciums per every 2 nitrogens. And again, we don't like these coefficients out front, so we drop them down. And the charges cancel each other out. So we're left with Ca3 N2. And that's it for writing those chemical formulas. Let's look at some other examples. So let's name these compounds. We got an SiBr4. Well, we know that SiBr4 does not include any metals. It's only nonmetals. So we are going to have to worry about prefixes. But because there is no prefix attributed to silicon, we can just name it silicon. So silicon is the first part of the name. And then we just have to look and see what the second part, which is Br4. There are 4 bromines. So the prefix attributed to 4 is tetra. And it's bromine, so we're going to have a brome. And because it's the second and the last element involved, it's actually going to be a bromide. So our name for this compound is silicon tetrabromide. Let's look at another one. Okay. This one has 4 N's, N's are nitrogen, and 10 O's, O's are oxygen. Well, we know what the prefix for 4 is, so let's go ahead and write this down. Tetra, nitrogen, you just simply name the first one. So tetranitrogen. And then looking up the prefix for 10, we can assign the next one as being deca. You could either write it as deca oxide, or conventionally speaking, they just do it decoxide. They drop the A when dealing with oxygen, just because it rolls off the tongue a little easier. No real specific reason beyond that. Let's do a couple more problems and then we'll be done. So write the chemical formulas for the following compounds. Carbon dioxide. I think pretty much everyone knows what carbon dioxide looks like in its formula. But just in case, we're going to look at carbon, which is a C, and dioxide, which means there are 2 oxygens. So O2. That's it. Carbon dioxide. Not too bad. This next one's a little more tricky, but not by much. Disilicon hexachloride. So, di is the prefix for 2, and hexa is the prefix for 6. So we write it Si 2 Cl 6. And that's the chemical formula for disilicon hexachloride. And that's it for naming compounds.